Algebraic warp drive, where Michael Algebraic shows his vessel accelerating and space actually curling up behind him, allowing him to go faster, use space as his acceleration force. Because in space, once you hit an acceleration force, it doesn't change. You need reverse thrusters to slow down. You know, there's no action of gravity. It's just the opposite. It's a reverse vacuum. Very well. I would have never thought of that. But what is it? It's a reverse vacuum drive. It's due to the vacuum of the drive being acting as the vantage point for acceleration and space travel. Now, whether or not space actually curls up behind you is one story. But as you can see, the force itself, the vacuum force, acting in not in sucking something up, but pushing it away. This false type vacuum is what allows things to be accelerated to the velocities they are. You know. So what does this mean? Faster than light speed space travel? Yes, it's possible. Okay, you just have to have the E content. You know, the way to make that force to be accelerate your ship. Now, that's the hard one, but due to the study, we know for a fact that we can travel faster than light. There's no brick wall. There's nothing there to stop us. Infinite mass doesn't exist because of the vacuum force. And you say, well, it doesn't mean it don't exist. It could be at 372,000 miles a second. Or it could be at 450,000 miles a second, which is the big G in space, because that's the big G. We're talking about gravity, that allows us to accelerate and move objects. But the thing is, everything's expanding. So every time you think you're getting somewhere, you're not getting there, because the numbers change. There has to be a consistency of the numbers for it to be valid. Since there's no consistency to the numbers, the value always changes. It's more and more and more. And so you go into AE's time travel idea. We never reach the speed of light, or twice the speed of light, because the numbers keep changing. Speed of light is the speed of light, but the numbers change makes our ability to reach those numbers change during the process of acceleration. You know, meeting that point.
This is not criticism against Einstein only, but Albert Einstein has become a household name. The history of relativity has been rewritten. I also say that all earthbound experiments are only good to the square of the ratio of the velocity to the velocity of light. This is not true for interstellar. That is, when it comes one way, you can get a first order effect. So what we would conclude from this is that clock B goes slower than clock A by V squared over C, or the opposite, clock A goes slower than B by the same amount. So which is it? So many years people have been thinking about these things and have invented types of Gedanken experiments, which are oxymorons themselves, because You don't get anything out of a Gedanken experiment that you don't put in. And there's things like the twin paradox, where one of the two brothers goes up into a space capsule, travels around, comes back to Earth, and sees that his clock has been running slower than his brother's, and that he's aged less. So in the 60s, there were titles in newspapers, "Space travel will make you younger." Things like this. And this caught on to the general public. That is, these things like this. But who traveled? The person that went into the space capsule, or the person that remained in Earth? Because he's still moving too, it's all relative. One to the other. So you can't say anything. Plus the fact there are accelerations involved, because he had to go out and come back. So going out and coming back, he had to slow down and speed up again. But relativists will say, no problem, that even acceleration has no effect on the velocities if we consider infinitesimal time intervals. This is not true. So the thing is that people have been looking also at models. How can we understand things like this? So a person called Herman Bondi, who took it from Withrow, who took it from Robb, without, this is what they call nostrization. Making it your own. Bondi didn't realize, give any idea of where it came from Robb at 1911, where you have Tom, you have Dick, and Harry. Okay? And we want to do away with accelerations. So Tom is stationary, and Dick is moving at a velocity v in this direction. Harry is moving in the opposite direction with a velocity minus v. And Tom synchronizes his clock with Dick's at a time t0. Okay? And at a later time, Dick synchronizes his clock with Harry at a time t1. Okay? Now the only thing that we have to assume here is that when the person is moving away from us, the intervals of emission, that is called the interval of emission I. So when he's moving away, this will be magnified by a factor of k. When he's moving towards Tom, Harry, the interval will be the opposite, 1 over k. Okay? So this is at the interval at which they arrive. Now, the distance from, say, t0 to t1 is t0 plus v t0 divided by c. Okay? This is the distance traveled. This is the velocity at which it's traveling, photons. Each of these have guns, photon guns, which emit photons. Now, the thing is that this is what Tom will see. And this must be equal to the interval at which it's being emitted times the number T1 over I of photons in this direction. So Harry, Tom now will see, since Harry is coming towards him, V0 T0 divided by C. The interval will be 1 over K times T1 over I. Okay? Obviously, the interval doesn't make any difference at which photons are emitted. And we can do two things with this now. We can multiply them together, and if so, we come out with T0 squared, 1 minus V squared over C squared, is equal to K, is equal to T1 squared. Okay? Showing that time now has been contracted. Or we can divide the two of them And in which case we have 1 plus v over c, 1 minus v over c, to the 1/2 is equal to k squared. K. Okay? This is time dilation, lengthening of time. This is the first order Doppler effect. Okay? Which of the two is more important for this thing? According to a person called Essen, Louis Essen, the inventor of the cesium clock, that T0 should be the same as T1. In which case, if I add a factor of alpha here to both of these things, of alpha squared, and alpha is the decrease in the emissions of photons, because if the photon, if Tom measures photons which are coming at him, which is reduced, there will be a factor of loss of ticks someplace. Ticks are being lost. This is according to Essen. I don't think this is a proper interpretation of it, because I just leave it as time dilation. Okay? Now, let's do the same thing now, looking at the Lorentz transformations. Okay? I have x. If gamma were 1, that would be just Galilean. And t equals t minus 4x over c squared. In Galilean terms, this would be equal to 0, and gamma would be equal to 1. And these would be nothing more than absolute time. If we multiply this by c and square that, we come out with the invariancy of the interval, okay, which is comparable time dilation. If we divide the two of them together and define velocity as x minus t equals v, which is equal to x over, we come out with I will call this one u. This would be u minus v over 1 minus u v over c squared. This was first written down by Poincaré. Later, it was generalized by Einstein when there was a difference, angle difference between the two Lorentz transforms. That is, that there were two different planes. This was generalized by him in 1905. But the original one was Poincaré. If you put in c for u, you come out with u prime is equal to c. This can no longer surpass the velocity of light. Okay? No matter which I choose to put c in. This would be the non-relativistic addition of velocities. And this is the relativistic addition of velocities. Now, back in 1909, Arnold Sommerfeld looked at this analogy with the analogy of hyperbolic functions. The hyperbolic tangent of a plus b, or a minus b, say, equals tangent of a minus tangent of b over 1 minus tangent a tangent b. Okay? Looking at the analogy of these two, I would just have to write v is equal to c tangent of some other v over c. Okay? This other v over c is a hyperbolic measure of the velocity. So as the hyperbolic tangent goes from 0 to 1. This is the ratio of V over C. The V, other V, would go to infinity. So the idea was that these new measurements done by Opera and CERN would be that the V they measured was not the Euclidean V, but the hyperbolic measure of the velocity, V. Okay? Now, the thing is that if I take the logarithm of this, of both sides, okay, and 1/2 logarithm of 1 plus V over C, 1 minus V over C, is equal to the inverse tangent hyperbolic of V over C. Okay? And this by itself would be precisely the length tangent of V over C is the Lobachevsky segment of length in hyperbolic space. So all this goes to show it's not space-time which is important, but space divided by time, or the velocity. And all this, as far back as 1909, could have been written down, was written down by Sommerfeld, and then quickly forgotten by the Gothic mathematicians. In a note, published in 1910, Kaluza, another name, known to string theory, suggested that the metric was not the metric that you write down for space, is dr squared plus r squared dv squared, if this is Euclidean, okay? If it is elliptic, it would be dr plus r squared and if it was hyperbolic, it would be dr squared plus this is the hyperbolic sign. R0 is related to the absolute constant, which in this case will be c. R would be the velocity, and if we go to a uniform disk, it would be r omega divided by c, would be the velocity. So in this case, dr squared is dr squared over 1 minus r0 squared. This is a stereogeographic factor which comes in due to the bending of space. Okay? Now, before leaving this topic, it's interesting to see that if I do the same thing here, and like this, r squared, 1 minus r divided by r0 times d squared. I consider disk a uniform disk and spinning uniformly with an angular velocity omega. This would be c squared here, same thing here. I consider the radius constant. This term would go away. And now I'm looking at ds is equal to r d phi over 1 minus. And I can integrate that from 0 to 2 pi, 0 to 2 pi. This would be the circumference of a circle, and this would be equal to r 2 pi over 1 minus r. So the circumference has become larger by this factor. So this was one of the predictions. Einstein was infatuated with a uniformly spinning disk. And he argued that if I lay rulers in the direction, in the radial direction, there should be no change. But if I lay the rulers tangentially, according to this, there should be a Lorentz contraction, and the disk should be larger, because I need more rulers to lay tangentially around. But this is incorrect, because if the rulers contract, so will the circumference contract. And I can't have any effect like that, observe any effect like that. In fact, if you call the inhabitants of this disk Poincarites, little two-dimensional beings, they walk around with clocks and rulers. And as they walk around the disk, their rulers will shrink or increase along with their bodies. So they can, and their heartbeats, so they have no means of distinguishing where they are on the disk. If they can communicate with each other, there is no way of telling where they are. And one of the most famous Gedanken experiments of Einstein was to put a local observer on the edge of the disk and another at the center. The center, obviously, is an inertial frame. So his clock will be running normally. The clock on the rim of the disk will be slower than that, and he will communicate that to the observer located at the origin. This is impossible. Two local observers can never communicate. It's all a matter of reference. To us Euclideans, we would see the distortions in these factors. But to the people living in the hyperbolic world, will not see any difference in the measurements that they make with their clocks or with their rulers. So, another problem was that if I write now this metric, so factor G, factor G squared minus some R squared times another 1 over G squared, we do that depending upon R. This would be a metric which would be a generalization of this one here, due to the fact, according to Einstein, that there would be acceleration. Now, this is divided into two parts. One is the spatial part, and one is the temporal part. Back in 1912, Einstein, who more often than not contradicted his own principles, was looking at the bending of light. Okay? Leonard, whose name is associated with the photoelectric effect, was very anti-relativistic in the analogy, pointing to the fact that the deflection of light by a massive object was done back in 1804 by a person called Solder. And the story goes that Einstein came up with a certain, due to the deflection of light in 1912. Thank heavens, the war, First World War, was approaching, and they couldn't get to Russia to do the observations. Only after the war, Eddington went to did the South Pacific, South Atlantic, did it, and found that there was a factor of 2 difference. Okay, the deflection of light, the advance of the perihelion of Mercury, were two of the most important results of general relativity. They are static. The other one is the reddening of wavelength, reddening of frequency in a gravitational field. I want to show you how Einstein obtained his first result. He began with nu is equal to nu 0, 1 minus b over c. Okay? This is the frequency of the emitter, this is the receiver, due to velocity v. Okay? He replaced this V is equal to G times T. G is the gravitational acceleration on the surface of the Earth, nu 0 equals. Okay? Then he considered a photon being emitted at a certain height, falling and being reabsorbed in a height h. He replaced T by h over c, and this becomes c squared. So now we've gone from uniform velocity to constant acceleration here, and we can go one step further. We can say that the acceleration times the height is minus the static gravitational potential. Okay? So we've come a long way from uniform velocity, uniform acceleration, to a static potential. Now, what does that static potential operate on? Well, according to Einstein, C is equal to C0, 1 plus E over C squared. But he just told us several years back that C was a constant velocity and not one in which varied with a position in a gravitational field. At the center of the coordinate system, we have C, 0. If we move out, we have C. So a clock will be, we must employ a clock which, when removed from the origin of the coordinates, goes 1 plus p over c squared more slowly than the clock used for measuring time at the origin of the coordinates. We will call c0 the velocity of light at the origin of the coordinates. Then the velocity of light at the place where the gravitational potential will be given by c. All I see here is a cubic equation to be resolved for c. Don't see anything else besides that.